Okay, so we are going to start with the first section, which is part 1. So part 1 is going to be mechanics and properties of matter. So mechanics and properties of matter. That is going to be our first part, right? And the first section of that is going to be dynamics. So we're going to look at dynamics right now. That's what we're going to start off with. The question comes, what is dynamics? From the word dynamics, you can see it comes from the word dynamo, which I think is a Greek word for something that is moving or something like that. So dynamics, when something is dynamic, it is ever changing. So when we are looking at dynamics, we're going to see things that are moving or changing, whether they're changing direction or whether they're changing in speed or velocity, whatever it's going to be. But dynamics is just things that are in motion. So we're going to be considering motion. This is very, very important. Either it's going to be motion in a circle or it's going to be motion in a straight line, but just know that something is moving from point A and it's going to point B, or it's going to be from point A and it's going to point B in a circle like that, or any type of motion as long as it's moving, right? What we're going to start off with, the first section, let me just call it I, is going to be motion in a straight line. That's what we're starting off with. Motion in a straight line. So as the name suggests, motion in a straight line is just motion from point A to point B in a straight line. So let's just say when it's moving from point A to point B, let this distance from A to B be denoted by S. So this object is moving a distance of S from A to B, right? And it's doing it in time t. Let it be moving in time t. So when I'm saying let it be moving in time t, it just basically means for it to get from A to B, it goes through t seconds. Let's just say t seconds. If it's 10 seconds, it's going to be 10 seconds. T is going to be 10 or 5 seconds, whatever it's going to be. So S is the distance, and then t is just going to be our time it takes, right? So we define something called velocity as, in simplest terms, let's first just say speed for now. Let's just say speed. Speed will be equal to, I think you already know that speed is equal to distance over time. We're going to see where speed is equal to velocity, but for now let's just say velocity, which is equal to speed, it is equal to distance over time. This is then given by, what is the distance between A and B? It is S. And what is the time it takes to move from A to B? It's t, right? T. So we have an equation. If V denotes our velocity, V is going to be our velocity. So V is equal to S over t. That's going to be our very first equation in this physics course. V is equal to S over t. It just basically means speed or velocity is equal to S over t. Why am I saying it is equal to? We're going to see later when we do some definitions of things called vectors and scalars. But for now, let's just say velocity is equal to speed. It is true in this case because of something very important that we'll see when we're doing vectors. So our velocity V is given as S over t, and that is motion in a straight line. That is very important. You understand the emphasis, why I'm emphasizing straight line when we do vectors, right? So velocity in a straight line is just given by distance traveled over time taken. That's how you calculate velocity, right? So let's see what we need to do as well, yeah? Just trying to fix something here. Okay, so that is defined as velocity. And we're going to define something called displacement. Displacement is defined as distance moved in a particular direction. So I'm just going to write distance moved in a direction. This is wrong English, but it just summarizes what I'm trying to say. It's distance moved in a particular direction, facing a particular direction. When you're looking at our motion in a straight line, the direction is this is facing B coming from A. This is the direction that we're moving in. So our S will be displacement if we consider that we are moving from A to B. That is the direction, right? Therefore, we are going to say our velocity, since this is distance, displacement is just distance, but on top of that we have a direction. And as we're saying, we're moving from A to B. So if S is representing displacement, it already has the direction because we said from A to B. That is direction, right? And what is the distance? Distance is that quantity. How many meters are there between A and B? You see what I mean? So displacement is going to have the quantity, which is the actual distance between A and B. And it's also going to have direction. Here, what is the direction? Direction is A to B. The quantity of the distance is going to be, where is B? B is here. Where is A? A is here. What is the quantity? What is the distance between these two? So quantity will be equal to distance. So my displacement is just distance in value and direction in where it's facing. So my velocity can now be, since I said velocity is also considering direction, so velocity can be defined as displacement, which is distance in a particular direction over time taken to move that displacement. Right? And now when we're looking at our equation, this one, V is equal to S over T, or this one here, we see that the units are going to be, let me write units here. What are the units for displacement? Units for displacement are just going to be meters coming from the distance quantity. The direction quantity does not exactly have particular units. You can say maybe 10 meters in the western direction or 10 meters in the eastern direction. It's fine. But when we're looking at least units for velocity, we're going to say displacement, it brings in the m, and then over time, which brings in the t, which brings in the s per second, because time is measured in seconds, displacement is measured in meters, and then in a particular direction, in a direction. So you can say meters over seconds in the eastern direction, meters over seconds in an eastern direction, the direction coming from the displacement part. So the units for velocity are meters per second. They can be written as this, or with laws of maths, you can write meters to the power of and second to the power of -1. This is the convention usually, ms to the power of -1. So when you're looking at this, when you're looking at velocity is equal to displacement over time, displacement is basically the change in the distance here. That is displacement, right? How is the distance changed from moving from A to B? So velocity, we can write velocity as equal to the change in displacement over, this is the better definition, change in time. This is a much better definition, because imagine we are on a Cartesian plane, our point A being here and our point B being here. A is not exactly the starting point of our Cartesian plane. Our starting point is here. So which means A has its own displacement and B has its own displacement from our starting point. They have their own displacement, the distance and a direction. For B, a distance and a direction. So when we say change in displacement, we want to say we were at A, which had its own displacement, right? But now we are going to B, which has its own displacement, which means the displacement has changed, moving from A to B. So it means it's better to say the velocity is the change in displacement moving from A to B over the change in time. Because maybe at A we had a particular time, T1. And when we moved to B, when we looked at our watch, our time was now T2, which means there is a change in time. Time from when we were at A to time when we were at B. So this is a much better definition to say velocity is equal to change in displacement over change in time. But this change in displacement over change in time can be called a rate. It is how much the displacement is changing per unit time. So when you say something is changing per unit, it means it can be written as, in this case, velocity is equal to, it becomes a rate, because a rate, something called a rate, is basically a change per unit of something. That is the definition. That is the definition of rate. Rate basically says change of something per unit of something. Here can you see we're saying change in displacement per unit in time, per change in time, per change in time. This division means per change in time. So our change in displacement is just going to be, our change in displacement over change in time is just going to be equal to rate of change of displacement. You can add per unit time if you want, but actually this per unit time is a repetition, because inside rate itself, this rate basically means per unit something. So this part might not be necessary, this per unit time. You can actually just say, when you say rate, it automatically means per unit something of change of displacement, which means this change in displacement is happening per unit of something. So this is the best definition of velocity. So I can write here definition. So definition of velocity is the rate of change of displacement. Straightforward like that. If you're asked in an exam, what is the definition of velocity? It's just rate of change of displacement. So as we said, displacement is magnitude or quantity, and it has a direction, right? Displacement is magnitude and direction, which also means that our velocity is going to have magnitude and it's going to take the direction of displacement. So if something is moving from here to there, it has this displacement, right? So which means when it's moving, its speed here, it's going to have a speed, right? It's going to have a speed when it's moving there. But when we're considering velocity, we'll be like, no, velocity also takes into account the direction. It's not just the magnitude. Speed, we are going to see these differences later. Speed will just be magnitude. How fast something is going. We do not care where it's going. Is it going up? Is it going down? Going up? Is it going left? Is it going down? Is it going... We do not care. For speed, we do not care. But when we are now talking about velocity, velocity is composed of the magnitude, same magnitude as speed. If this is 50 kilometers per hour, our velocity will have the same. When we're converting it to velocity, we have the same magnitude, 50 kilometers per hour. But with velocity, we go another step. We include the direction. So if it's 50 kilometers per hour going up, for speed, we just say 50 kilometers per hour. But for velocity, we say 50 kilometers per hour going up. We have to include the direction, going up. 50 kilometers per hour going to the left. Whatever direction it is, going east, going south, southwest, whatever direction it is. So that is our velocity right now. So this was just an introduction to velocity. Later on, we are going to, in the next video, we are going to now get into but no, before I close this off, let me make sure that I just do this part before I close this. Let me delete everything because I think my page is finished. Oh, I have a page here. Okay, let me talk about something called uniform velocity, because it's just good to put all definitions of velocity into one before we move on to vectors and scalars. Because if I move on to vectors and scalars, maybe this will make better sense. So uniform velocity is when an object travels equal distances. So this happens when an object travels equal distances in equal times. No matter how small these distances may be. So if I travel 50 meters every second, I'm traveling 50 meters every second. Every second I'm just traveling. These gaps are 50 meters each. So every second I'm traveling 50 meters. It means I'm moving with uniform velocity. It makes sense. The name itself makes sense. Uniform. It's uniform, not changing. It's not changing. It's constant throughout. Every second I travel 50 meters. Every second 50 meters. Every second 50 meters. Every second 50 meters. Equal distances in equal times. Equal times being the 1 second that I'm talking about now. Equal distances being the 50 meters, right? So if that small change in distance, let that small change in distance be equal to delta S. This delta, I think it's called delta. This delta S, it just means change, right? So if it's change in S is given by this delta S, and then if my small change in time, is equal to delta T, it therefore means that my velocity, my velocity is change in S over change in T. If you remember, that's how we defined velocity down here. We said velocity is equal to change in displacement over change in time. That's the same definition coming up here, but in mathematical notation. Change in S over change in time. Then there's something very, very interesting in maths called the limit. The limit concept. So basically the limit concept says, if our changes in time, you remember my changes in time, I was saying 50 meters per second, so my change in time was 1 second, right? I was increasing my count by 1 second. But what if I had considered 0.5 seconds? What the distance is traveled in 0.5 seconds? What if I considered distance traveled in 0.2 seconds? 0.2 seconds. Or distance traveled in 0.1 second. Every 0.1 second, I measure what distance I'm moving in. How have I changed my distance in 0.1 every 0.1 second? So when it says 0.1 second, I measure my distance. In 0.2 seconds, I measure my distance and I calculate the change here. When it goes to 0.3 seconds, I also calculate another delta S here. What would then come out is something very interesting, which is called the limit. And the limit is basically saying, if I push this delta T, or the change in time, towards a very, 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 very small number. So I'm going to push delta T towards 0. You see here, I pushed delta T. Originally it was changing in 1 second each. Now it was changing in 0.5. Then I pushed it to 0.2 to consider the changes in distance when it's now 0.2. Then I pushed it further to 0.1 second. So if I keep pushing it down to consider very, very small changes in T, I do something called a limit. So I'm going to say limit, as I push my delta T towards 0, I'm going to consider the limit of this thing now. So the limit of this, if I push my delta T towards 0, if you're doing a calculus course in university, or when you do it in university, you understand this better. But this is just to show you where this is coming from. So when you push this thing towards 0, this bottom part towards 0, this whole thing changes to something called ds over dt. And this becomes a differential. Probably by now, maybe you haven't done differentiation, or you've just done it a bit. This is just simply differentiation. So differentiation is defined as just a limit. So when I push my t towards 0, I create something called a differentiation. So I'm now just differentiating my delta s, my s over t. So my d by ds becomes my velocity. That is the proper definition of velocity. Velocity, you're considering very, very small changes of time and trying to see how the displacement is changing. How's the displacement changing? In very, very, very tiny changes in time. That is your velocity. That is your proper measurement of velocity. So v is equal to ds over dt, or in simple terms, it's just going to be delta s over dt. If you want to be a calculus guru, you say this is the limit of delta t as delta t approaches 0 of this thing here. That's what it is. So we have defined our uniform velocity. That's the concept I wanted to define. Uniform velocity happens when an object moves equal distance in equal times. That's basically it. That's just it, right? So in the next video, we're going to consider things called vectors, and we'll see the difference between velocity and speed, and then build on as we are going to see other vectors now that we're introducing, like acceleration and forces. So see you in the next video.
Created with free version for non-commercial use.